Hi, my name is Rupak.
My name is Siddhanth,
And my name is Vihar.
and today we're presenting our final demonstration for ECE 547 Spring 22 Tiny VM, a small scale voting machine. Our demonstration will include first a real life mimicking of how voting takes place using the machine we've built ourselves. And you can go ahead and see the video now.
I will be the voting official. You are a legitimate user.
So I have my correct card
Please cast a vote.
and I got my OTP here.
Candidate 1 selected. Vote registered.
And I got a notification that my vote has been registered.
You are a legitimate user.
I'm a legitimate user, but I have an invalid tag.
Invalid tag.
As you can see on the screen, I cannot vote. I can click on any candidate, but it will not let me select a candidate. All I can do is click exit and leave the voting booth.
You are a legitimate user.
I'm also a legitimate user, but I have a stolen card, so I don't have the
Please
one-time
cast a
password.
vote.
I'll put in a random one-time password.
Candidate 2 selected. Incorrect one-time password. Vote discarded.
As you can see, my vote was discarded because the OTP wasn't correct.
You are a legitimate user.
I changed my clothes and came back, but I've already voted.
You have already voted.
So again, it won't let me.
Candidate 1 selected.
It won't let me cast my vote. I can only press exit.
And now for our final use case.
You are a legitimate user.
Please cast a vote.
As you can see, I got my OTP. My OTP, I have inputted my OTP. But I do not want to vote for any candidate. So in every election, you have the option of not voting for any of the candidates. So I'll put my correct OTP in and just click submit.
Vote registered.
And this verifies the nota option, and I've also gotten my confirmation message. Okay, now that you've seen the video, we would like to explain the technical aspects of our project and how we implemented what we implemented. In this slide, you can see the entire device that we built. You can see that it comprises of 4 different parts. The first is our Raspberry Pi 4, which is our central brainstem, and it handles everything that our machine does. It is connected to a speaker, which we implemented to make sure that this machine is accessible for visually impaired users, voters as well. The 5-inch Raspberry Pi touchscreen is used to mimic a real-world voting machine in which you touch and press the button for your selected candidate for your vote to be registered. And lastly, on your bottom left corner, you can see is an RFID reader. The RFID reader is used to authenticate a user and is used for the first part of our auditability aspects. Auditability can be divided into 3 aspects. The first aspect, which we will be discussing, is voter confidence and tampering with elections. To enable voter confidence, we are implementing 2-factor authentication. The first factor, as you can see in the slide, is RFID verification. The white card you can see is mimicking a U card for a student. And once the student is tapping, and if they are in the central database, which in our case is their Spire database, then the user is allowed to cast a vote, as you can see on the touch screen. This also helps us enable less tampering of the election, as if you cannot, and if you're not registered as a voter, then you cannot cast a vote, hence not tamper with the election. The second factor that we implemented to authenticate the user's identity, thus increasing voter confidence and decreasing tampering of elections is the implementation of a one-time password. As you can see in the bottom message on this screen, as soon as the voter scans their RFID card, and if they are registered, then an OTP gets sent to their registered mobile phone, which is also a necessity that we have to do as students on Spire. And they get an OTP like this. They input this OTP on the voting interface, and if the OTP is correct and if they are registered, then you can cast a vote. Once the vote has been casted and everything is complete, the voting process is complete, you will get a confirmation message, as well as you can see on the top message on this screen, which shows that their vote was registered in our database as well.
Now I will explain the different possibilities of voting. As soon as a student or the user presents a RFID tag or the U card, the machine takes the hash of the RFID tag and finds it in the list of all the registered users. The registered users file contains the hash of all the RFID tags, and if the machine is able to find a match and detects that they have not already voted, then the machine pulls up the graphical user interface and allows the user or the student to cast their vote. But before they could submit their vote, they need to enter a one-time password, which is sent to their phone. This enables two-factor authentication. Just in case the card gets lost or stolen, the adversary won't be able to provide the correct one-time password, and hence the vote would get discarded. But in case the legitimate user wants to cast their vote, they would be able to provide the correct one-time password, and hence their vote would get registered. A machine also offers an option called NOTA, which stands for none of the above. In case the user or the student doesn't want to vote for any of the candidates standing in the election, then they have the option to not to select any of the candidates and simply press the submit button. The next case is when a student or the user presents a tag which is not identified by the machine. In that case, the machine simply shows a message that the tag was invalid and they're not allowed to cast a vote. All they could do is to press the exit button. And the next case is when the user tries to cast their vote more than once. In that case, the machine shows a message that you have already voted, and again, their consequent votes are not counted and they get discarded. So this is how our registered users.csv file looks like. It contains the hash of all the RFID tags. And we are assuming that a machine would be used for small scale elections like campus elections. And we are also assuming that we have the data of all the students like the Aspire IDs. And this type of data cannot be made public. That's why we are hashing the RFID tags. And this file also provides recount, the option of recounts, because it makes sure that the total number of votes casted should not be greater than the total number of registered users. Lastly, we have different CSV files for different candidates. These provide better auditability, and also these files get dynamically updated throughout the process of voting, and hence it also enables surprise recounts.
So moving on to the encryption. So as Rupak mentioned that all the votes are counted, the votes are counted in a CSV file for every single candidate. We cannot store the tag IDs or who voted for who, but we only count the ASCII time and of when the vote is registered, and the ASCII time is noted in the CSV file. This is an example of a candidate 3 CSV file. As you can see, 2 votes have been casted for candidate 3, and the ASCII time of when the vote was registered are noted. This is an example of a decrypted file, and we are doing encryption because information like this cannot be made public. When we encrypt this file, we get something like this. And using this, not only is the timestamp now encrypted, but also, since it is only a single row, an attacker cannot find out how many votes are casted for this particular candidate based on the encrypted file. Similarly, we have a file called check.csv, which contains the data of all the voters who have already voted. Again, the encrypted version of this file is just a single line, no matter how many lines the decrypted version would have, which would denote the number of people who have already voted. When it comes to the third factor of auditability, which is separate voting and tabulation, we are taking care of that using two different working directories. The working directory for the process of voting and the working directory for tabulation are different. As you can see in the screenshot, we have CSV files for the four candidates, the voters who have already voted, the key for encryption, and main.py, which is a file which helps in recounting, which could be done by election officials, as well as the decryption of all the CSV files. All of this is in a separate working directory called output, and the process of voting takes place in the working directory called voting machine. This directory has all the functions for encryption, the database of all the registered users, and a file called votingmachine.py, which is basically running the entire process of or the entire process of voting, which starts from the reading of RFID tag all the way to registering a vote. So at this time, the vote is being casted in votingmachine.py, and we are in the working directory of voting machine, and the tabulation happens in output working directory, which contains all the CSV files for our candidates. The recount can also happen using a separate directory, and by this we are ensuring that the process of voting and tabulation are always in two different working directories. So now we'll talk about our contributions.
My contribution to this project was to gather and assemble all the hardware components. I interconnected the Raspberry Pi with the RFID reader, the touchscreen, and the speaker. I also created the graphical user interface for the project. I used the Python TK interlibrary instead of the Pygame library because it has a lot of bugs. I created a custom function to make rounded buttons so that the graphical user interface looks as similar to a voting machine, the actual voting machine, as possible. And I also implemented the one-time password, or the two-factor authentication mechanism, along with the message that a user gets on their phone when they successfully cast a vote.
In this project, I was responsible for implementing the speaker text-to-speech commands to be implemented for specially abled and make our voting machine more accessible. I was responsible for using the PyTTSX3 library, Python speech to text one, in which we just combine the syllables together and are not using the internet at all, which made our system more robust, reliable, and more secure.
I contributed by enabling all the encryption of all the CSV files and the hashing algorithms. I did this using the Fernet module of the cryptography library, and documentation for this is all available in the official Python 3 documentations. I used the predefined libraries so that any function that I create can be successfully audited by a third person, and all the source code is publicly available for everyone to check. So
Okay.
that is our project. Thank you so much for watching.
Thank you. I would lastly, before we conclude, I would like to say that our entire project was able to completely use all the materials we learned in 547. We have implemented hashing. We have a smaller TCB. We were able to use RFID tags. We have a clean, small code base. We are implementing separate vote casting from tabulating. We are showcasing transparency, and we are enabling recount. We have voter confidence. It is harder to tamper with elections, and we are enabling surprise recounts. So our machine is complete, and this is our demonstration for ECE 547. Thank you.